You're getting it. All right. So yeah, fluid mechanics. Let's re-put up some of our basic definitions. So density. Density is
M over V.
mass over volume. So it's kilograms per meter cubed. Mass over volume.
Okay.
Right? And then we have pressure. This is a P, not a rho. Pressure. Pressure, what's that?
Tangential force over the surface area.
Yeah.
Force perpendicular to it, not tangent to it, perpendicular to it.
Yeah.
Perpendicular force over area. If I've got some area, then the force that puts pressure on it is the force that points directly down onto that area. The force that's perpendicular to it. Right?
Yes.
Okay. And then we derive some of these pressure equations, so let's really quickly rederive those to help get us back. So I've got some container of fluid, and we're going to look at some arbitrary piece of liquid inside of here.
Okay.
So I'm going to look at this block of liquid. Okay? And it has area A on the top and the bottom. And we're going to look at all the forces acting on this ink. So pushing down on the top of this ink, we have
Weight of the water.
Pressure.
Yeah, that's what I meant. We're going to look at all the pressures acting on this ink.
Oh, okay.
So let's start from the bottom actually, because I'm going to call this point right here my XY axis. Good? So I'm going to go up. So starting right here, we have a pressure pushing up on this ink of,
Just your pressure, right?
oh, sorry. The water's holding still, we're writing out the forces. Don't let me keep mixing myself up.
We're writing
out the forces,
Okay.
yes. Because we know that this little bit of water inside this container, this little cube of water, isn't moving. So we know that some of the forces on it are going to be
Zero.
So that's what we're writing, the forces acting on this ink. So from the bottom, we have a force acting on it. The force is equal to the pressure times the area. Okay? So we have P times A right here, pushing up on it.
Same with the top, right?
At the top, it's going to be slightly different. The pressure, so I may call the distance from here to here, I may call that distance dy, some infinitesimal change in y.
Okay.
And so by the time we get up here, the pressure could have changed ever so slightly.
Infinitesimally small.
So we're going to say P plus some small change in pressure times A. And we know that in this case, dP is going to be negative. It's going to get slightly smaller.
Oh, that makes sense.
But dP is some infinitesimal change in the pressure, right?
Okay.
So if we look at all the forces in the y direction, we have, we're calling that way
Out of the water.
Huh?
What about the weight of the water?
Yeah, I was going to write that in there. I didn't know if we wanted that as a picture in here. But yeah, we also have the weight of the water pushing down with dW. Since this is an infinitesimal bit of water, it has an infinitesimal weight dW, the weight of the water.
Yeah.
Okay, so when we look at the forces in the y direction, all the forces in pointing up perfectly cancel out with all the forces pointing down. So I know that pressure times area is equal to pressure plus our infinitesimal change of pressure times area plus dW, an infinitesimal weight.
Yeah.
With me so far?
Yes.
Okay, now we're going to expand on this dW term. What is our infinitesimal weight?
It's the infinitesimal mass times gravity.
dm times g. Okay. Good. How else could we represent dm? We want to somehow get the dy in there. That's ultimately what I'm trying to do. I'm trying to re-represent dw in terms of dy. Because when I integrate my pressures, I'm wanting them to change with respect to y. So I'm going to keep fidgeting with this term until dy comes out.
How do you fidget with a mass to get a position?
Oh, you get volume.
Yeah,
versus
there we go. Okay, we can think about it in terms of volume.
Okay.
So we can say that this is dV times m,
over.
not m, sorry, times rho, our density, times g, right?
Okay.
This is mass per unit volume,
Mhm.
and this is volume, so together they give you mass.
Yeah.
Okay? How else can we mess with it? Is there a way I can write dV so that has a dy in there?
Well, dV has your x, y, and your z, right?
Look at on here, what is dV? So dV is the volume of this scene right here, right?
It's your area times your dy.
Perfect.
Okay.
So this is just, this whole thing is then is going to be equal to your area times rho times g times your dy, where your dy and your a together gave me dV.
Okay.
Follow that?
Yeah.
So now I'm going to rewrite this equation. So I have P times A is equal to, I'm going to multiply this out. So it's equal to P times A plus dP times A plus A times rho times G times dy.
And you can just get rid of a.
We can get rid of A. Doesn't matter which way we do this. First I'm going to subtract this from both sides.
Okay.
Oh, that's smart. Yeah.
So subtract this side, this, and this from both sides. And we can also divide through by A. So divide both sides by A, which gets rid of that A and gets rid of that A. So what we're left with is, I'm going to write dP here, and then I'm going to move this to the other side.
Wasn't
Is
dW
equal to
negative?
negative rho times G times dy. Sorry, what's that?
Wasn't dW negative? Because it's going down on the y-axis.
No, I did all the y forces are equal to, all the forces pointing up are equal to all the forces pointing down.
Okay.
I could have done this minus that is equal to 0, but then just move those to the other side.
Okay.
Good?
Mm-hmm.
Okay.
Okay, now we're going to mess with this equation in two ways. So one way I'm going to rewrite this equation, just for note, and we'll come put it over here, is that dP dy is equal to negative rho times g. The change in pressure with respect to your height is negative rho, where rho is the constant of the material, or where rho is the density of the material, times g, the gravity that you're talking about. Negative meaning the higher we go, the less the pressure gets.
Yeah, that makes sense.
Okay. So that's one way we could manipulate this. The other way we can manipulate this is, we don't really need this version of the picture anymore, so we erase that. If dP is equal to negative rho times g dy, then if we add up all our dPs from point 1 to point 2, so from point 1 to point 2,
Yeah.
and we add up all our changes in pressures, that will give me the total change in pressure from point 1 to point 2. And that will also be the total changes in these seams, where our dy changes from point 1 to point 2. In other words, I'm going to integrate both sides of this equation now. I'm going to integrate this from point 1 to point 2, and I'm going to integrate this from point 1 to point 2.
Mm-hmm.
Yeah.
Okay? So if we integrate our pressure from point 1 to point 2, that's just going to give me the pressure at point 2 minus the pressure at point 1. Right? For this integral, I can pull the minus rho times g out, and now we're just integrating dy, and that's just going to be y2 minus y1. Our height at 2 minus our height at 1. That's our change in height.
Okay.
Good so far?
Mm-hmm.
Okay, that's our next equation. P2 minus P1 is equal to negative rho times g times y2 minus y1. Okay. Set up one more picture here, and then we're going to plug into this equation. So we came up with that equation, we're done. Now I'm just going to reuse this container here and set up a different scenario really quick. So a scenario we're often interested in is the change in pressure from the top, which we say has pressure P naught, down to some depth H down here.
Yes.
So this is P naught, we're looking for the pressure at P. This is also height Y1, or y naught, we'll say. And this is going to be at height y1 now.
Okay.
You with me? So if we plug that into this equation, let's see what we get. We get P minus P naught is equal to negative rho times G times y naught minus y1. Good so far?
Mm-hmm.
Yeah.
Okay, now notice what is H? H is equal to y naught minus y1.
If you're saying this is your y-axis.
Here's my xy axis. Y naught is a higher value than y1.
Don't you want to do?
Oh, yeah. Duh. Okay.
So this is our equation when we want to think about going up in the material. I'm setting up an equation for when we want to think about going down some depth h.
It's not what we did yesterday.
Doesn't matter.
You have y2 minus y1, and then you have y naught minus y1 in your equations.
Oh, thank you. That doesn't matter. I need to keep the order the same.
Okay.
We have P2, yes. Okay, thank you. That was a mistake. Plugging into this equation, it comes out like this.
Yeah.
Nice catch. Good so far?
Mm-hmm.
Now h is equal to y naught minus y1, or in other words, h is equal to negative y1 minus y naught.
Yeah.
Good? So when I come and I plug h into this equation, p minus p naught is equal to, it's y1 minus y naught is h, but then it has an extra negative, so it's going to cancel out with that negative. And so we have rho times g times h. Good?
Mm-hmm.
And so that gives us then that our pressure is equal to our initial pressure at the top plus rho times g times h. And that gives us our pressure change if we go some depth h into the fluid. So this is thinking about it in terms of going down some distance h. This is just, or this one's just giving me the change of pressure between two heights.
Okay.
Make sense?
Yeah.
They're really doing the same, it's really the same equation, those two. It's just two different ways about thinking about the same equation. Okay, so those were some of the basic equations that we had set up. And then we talked about buoyancy, a buoyant force. Now, how to think about buoyancy. So, the way we think about it, I should have left my container drawn here, some container of fluid. And we take some arbitrary shape inside that container. We're looking at the water, pretend this is water, but it could be any fluid. We're looking at the water right here. Right, some random piece of water. Now that random little piece of water is not moving.
Okay.
Right? So if we were to add up all the forces acting on that shell of water right there, that piece of water, then those forces would come out to zero. So all the forces in the x direction pushing this way are perfectly canceled out by all the forces pushing this way. And all the forces on the top of the sink are perfectly canceled out by all the forces pushing on the bottom of the sink.
Yeah.
With the exception of, and its weight is also pulling it down. So in the x direction, that's pretty trivial, but in the y direction, if we look at all the forces in the y direction, what do we have? I have that all the forces acting on the bottom of it, all the forces at the bottom, are equal to all the forces at the top plus the weight of the water there.
Yeah.
And I don't know if we want to write that with a rho in it. We could also rewrite this as the forces that, well, we'll get there in a second. So question, what is greater? The forces pushing at the bottom of the water or the forces pushing at the top? Or are they the same?
They're the same if it's
The ones
stagnant.
that pushing up.
The ones pushing up are greater than the ones pushing down. Because the ones pushing up not only cancel out the ones pushing down, but they also cancel out the weight.
Oh, duh.
So they differ by mg. Okay.
Okay.
So if I were to take the forces at the bottom and subtract all the forces at the top, that is still equal to mg. So the forces at the bottom are greater than the forces at the top.
Yes.
And the difference in these forces are what we call the force of buoyancy.
Okay.
So the force of buoyancy is equal to mg here. I would do F sub b, but we already did that for the forces at the bottom. It's equal to the weight of the water right there. And another way that we can write this, if we want, is we could also write this as its density times the volume of that water times g, which is probably the way that will be most useful.
Yes.
How do you spell buoyancy?
Bu and then buoyancy.
How do you spell buoyancy?
Oh, wow.
B-U-O-Y.
So rho of our fluid times the volume times g will probably be the easiest way to see that. Oh, we skipped over something. And it's B-U-O-Y buoyancy. I think. B-U-O-Y-A-N-C-Y. Yeah, that's right. But yeah, the way I always remember it is buoyancy. Because it doesn't make sense to my brain that the U should be in there.
Yeah.
Anyways, so if the force of buoyancy is equal to the density of the fluid. This is an equation in the book, but it might just be a useful one to have. Times the volume being displaced times g. So notice what that means. Imagine now that I take this object here, or I take that water, could still have that in there, I guess. I take that water and I suddenly replace all that water with that exact shape, that exact volume, and I suddenly replace it with wood. Right?
Mm-hmm.
And I want to know, what's the force upwards going to be?
A lot more than your force.
It's going to be the force of buoyancy minus the weight of the wood.
That's if you replace it?
Yes. So the water, notice that the fluid around this object doesn't care what that actual object is. It's going to push the same hard no matter what.
Yes, that makes sense.
And how hard is it going to push? It's going to push this hard. It's going to push with the force of buoyancy.
What if you put something like paper underwater?
Well, paper absorbs water, and so it's basically going to have the density of water at that point. I think.
What if it's something like steel?
It's still heavier than water?
Falls, yeah.
Then it falls.
Oh, okay. Yeah. That makes sense.
If it weighs exactly as much as water does, then it stays there, because it weighs exactly as much as the buoyancy force is pushing up. If it weighs less than water, then the buoyancy force is going to push it up. If it weighs more than water, it's going to overcome the buoyancy force and still fall down, even though buoyancy is still pushing it up.
Is there an object that is just the same as water? And it will stay still if you put it in water?
You can easily make them. You can make 100 of them.
Just make it?
Sure. Take something that's composed of steel and wood and get your ratio right.
Oh.
Steel's more, wood's less. Get the right ratio, you got water.
Put it in the ocean and
Real
just
easy to
stay
do.
still. It's kind of cool.
That would be cool. You can make like an underwater house that just stays there.
It's what things like fish have to do. Fish have an empty cavity inside of them, which makes them naturally want to go up, and so there's also really dense parts of fish to help cancel that out, to keep it down inside the water.
And their bodies naturally do it for them?
Well, it's just what they're composed of.
Interesting.
And I'm sure they have ways to regulate it, but
How much air do you have to have in something to make it float?
it depends on the thing. I mean, if there's a big, the Titanic's going down, and you run to the bottom of the Titanic and go, it's not going to go back up. So you need enough to change the density of the whole object to the point where its total weight is less than that of, or its density is less than water. Anyways, the last thing that we forgot to recap from last time is, since pressure is equal to force over area, well, remind ourselves of Archimedes Principle. So Archimedes Principle says, and we'll draw this. So this is a fluid, this is a fluid. Archimedes Principle basically says, pick a height, the pressure is the same as the height across your fluid. Right? Mm-hmm. So here's some fluid distributed across this container. Over here has area 1, over here has area 2, and the pressures here have to be the same. So if we had a piston here, and I push down on that with some force to create some pressure at the top,
Yeah.
and this is also covered by some piston, then it also produces a force over here. So we'll say this has area 1, and I put a force down on that piston of F1. Then there's going to be a resulting force over here of F2 to keep the pressure the same. F2. And so we can calculate F2 in terms of F1 and as a ratio of the areas, because I know that F1 over A1 is equal to F2 over A2. So if I want to calculate F2 in terms of F1, I know that F2 is equal to, multiply both sides of this equation by A2. So F2 is equal to A2 over A1 times F1.
Okay.
So if I know that A2 is 1,000 times bigger than A1,
Yeah.
then that means that F2 is equal to 1,000 times the force I apply at F1. So if I apply a force here of 100 newtons, then over here there's a force being applied up of 100,000 newtons.
That's right.
Oh, that wasn't Archimedes' principle, sorry. That was Pascal's law. Pascal's law. Pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. Okay. Archimedes' principle was one that had to do with buoyancy force,
Yes.
right? Remember the Archimedes Eureka story?
Mm-hmm.
Bathtub.
Yep, in the bathtub. Okay. So now we get to I guess that's kind of a side note, surface tension. One of the things that we ignore in this section is surface tension, but it's worth mentioning that there is surface tension, and that water has surface tension. Something you're very interested in a chemistry class. I don't know if we'll do a lot with surface tension in this class. I can't think of anywhere in particular that comes up.
Okay.
But if you look closely at a water molecule, first off, what is water composed of?
H2O.
H2O, what is that?
Water.
Hydrogen and oxygen.
2 hydrogens and 1 oxygen.
Yeah.
Yeah. So what that looks like is we have an oxygen atom here, and then we have 2 hydrogen atoms which come off like this, and no doubt you've seen pictures of that 100 times. We call them Mickey Mouse, right?
Yeah.
So here's your oxygen, here's your hydrogen. Now what happens on a smaller scale is, not a smaller scale, let me kind of draw the same picture again, but here's the nucleus of the oxygen atom, and it has its protons and neutrons, right? And it has its electrons orbiting around it. And together, the net charge of just an oxygen atom is 0. It's not positive, it's not negative. The electrons and the protons together perfectly cancel each other out for a net charge of 0.
Yeah.
And then we also have a hydrogen atom, which is just one proton, which is positively charged, and one electron orbiting around it. And so we have one proton here, and one electron orbiting around it.
Doesn't it have one neutron as well?
It can.
Oh.
That would just be a different isotope. But by definition, if it has one proton, it's a hydrogen atom. So maybe there's a neutron attached, maybe not. But that's how they are in nature by themselves. But when the hydrogen bonds with the oxygen, then it shares its electrons with the oxygen.
Yes.
And so you can kind of think about it. I mean, this is super inaccurate, but good enough to give intuition.
Okay.
You can think about the electron now orbits both of them. And this one's electron now orbits both of them. And so they share their electron with the oxygen atom. What that causes is now, around the oxygen atom, since those electrons are spending some time down here as well, that makes the oxygen atom have a slightly negative charge sometimes down here.
Okay.
And since sometimes there's not an electron up around this atom, since it's going around here, then sometimes there's a positive charge around this and a positive charge around this. And so water has a little bit of this dipole going on, where it's negatively charged at one end and positively charged at another end.
In instances.
Huh?
So not all the time, right?
All the time. These are going so fast that, again, lying to you a lot to give you the right intuition. These are going so fast that there's kind of like a permanently positive charge up here and a permanently negative charge down here.
Okay. That makes sense.
Okay? And so what that causes to happen is, well, didn't really need to erase that. Guess I can draw it smaller. Is here's a water molecule. Water molecules stick to each other. And so another water molecule will come and stick on it like that. And another water molecule will come and stick on it like that. Because the positive ends here attract the negative ends of other water molecules.
Yeah.
Right? Different charges attract each other.
Mm-hmm.
And so water sticks to itself a little bit. And that sticking phenomena, we call it surface tension. It causes water to stick to itself. That produces a surface tension. You probably have noticed before that if you have a cup of water and you're really careful, you can actually fill up the cup of water fuller than the sides of the cup, and you can get the water to stick out some. That's because the water sticks to itself. If the water didn't stick to itself, that wouldn't happen. It would just flow out. Try to do the same thing with gasoline.
Gasoline does the same thing?
No, it won't do it like that.
No.
Huh?
Are you recommending I try that with gasoline?
Sure, why not?
Okay.
You'll stink for a day, but hey. Anyways, so that's what produces surface tension, and that's what we mean by surface tension of water. It's its tendency to stick to itself. And you notice this all the time. I go put my finger in water, and there's like a drip hanging right there. Why doesn't it just fall off? It's sticking to itself.
Yeah.
Gas doesn't do that?
It sticks to itself a little bit. Everything sticks to itself a little bit, but much less than water.
Okay.
And alcohol solution shouldn't do it as much either. It's like rubbing alcohol.
Sure.
Anyways, so that surface tension, kind of just a side note here. I don't know if we come back and do any calculations with surface tension later, like calculating the size a raindrop should be or anything like that. But that's why raindrops come down in little spheres. And the pictures you've seen of raindrops are big old lies. The raindrop does not look like this. It looks like this.
For real?
Yes.
Even with
This is a
gravity
bunch
pulling
of
down?
water gathered up, slowly sliding down something, like a tear. But no, a raindrop just looks like a little ball of water.
Wow.
Kind of like how stars, like the sun, it's not really in the shape.
Wait, really?
Well,
It's
that's
just the way that
obvious.
it's portrayed. It's really just a sphere.
That's crazy.
All stars are just spheres.
Can raindrops be like elongated though? Or are they all perfect circles?
They're going to try as hard as they can to be perfectly spherical. There could be other circumstances, like maybe the wind just happens to be blowing a specific way to create some sort of shear on a raindrop to stretch it out. Yeah, that's possible. But in general, it's trying to just be a little sphere. And if you were to go out into space where there's no gravity and you were to dump out water, it would just grow into a ball.
Yeah, I've seen stuff like that.
Okay, so now we move on to fluid flow. Fluid flow, let's see.
What would happen if you dumped water in space and put a fish in there?
Say that again?
If you dumped water in space and it stayed in the ball and you put a fish in there, would the fish live? Or would the space have some effect on the water?
The fish could be in the water, yeah,
Where would it live?
for a time. I mean, it needs more than just water to live, but yeah.
Interesting.
That's good.
So you can help.
I mean,
with
there still needs to
aquarium in
be
space.
oxygen in the water. Fish have gills.
I wonder if you made fish tanks like that from the space stations.
That'd be legit.
That would be so cool, just floating water. And you just oxygenate it every now and then.
Okay, so where does he have a good picture of this? Guess I'll just have to try and draw my own picture. Okay, so now we're going to think about water flow, and since it's easiest to kind of think about water flowing through a pipe, that's often how we're going to think about it.
Okay.
And I'm often going to draw the pipes that the water is flowing through like this. Just to say, at one point, the water is flowing through an area like this, and then somewhere down the road it's flowing through an area like this.
Okay.
So kind of ignore that little bit. It's just somehow transitions from being this to being this. This is what I'm going to do over and over again. You with me?
I think so.
So, some pipe. At some point it's this thick, go down 100 yards, at some point it's this thick now.
So just
Something like that. It just changes somehow. The thickness of the pipe changes.
Oh.
That's all that matters.
Okay.
The cross-sectional area of the pipe is changing. And I'm going to draw the cross-sectional area as just a line, but that's really a circle, right? Because it's inside of a circular pipe.
Yeah.
Okay, so this has cross-sectional area. We'll call that A1. This has cross-sectional area. We'll call that A2. Good so far?
Yeah.
Now, looking at a pipe right here, after some time dt into the future, we have some water flow through this. How do I want to draw that? Maybe just a dotted line. So we have water flowing through this cross-sectional area, and in one infinitesimal moment of time, this much water goes through this area. You with me so far?
Mm-hmm.
Let me move this line.
Goes
Here.
through or is in?
Goes through. So there's water flowing through the pipe this way, right?
Yeah.
And I run my stopwatch for a split second. And in that time, the water that was here is now here.
Okay.
And so this much water has flown through this surface, or that cross-sectional area.
Mm-hmm.
Make sense?
Mm-hmm.
Yeah.
Okay. And let's calculate that really quick. How much water that is. Now let's pretend that the water here is flowing with velocity v1.
Okay.
So the volume of this water then is going to be this distance right here times A.
Mm-hmm.
Yeah.
And that will give me the volume. Okay, so we'll call that this distance right here. What is this distance right here?
Sure. Yeah, your dx.
But how can I calculate that from v1 and dt?
V1 times dt.
It's just v1 times dt. Perfect.
The velocity times a
Time, if I'm going 10 meters per second for 10 seconds,
oh, okay.
there you go. Okay, now, but what we actually want is, I want to figure out what dm is. I want to figure out the infinitesimal amount of water that got through there. and that's going to be rho times dv, which is going to be rho times A times V1 times dt, right?
Okay.
Move this V1 down. And hopefully, I'll try and do all my velocities with curly V's like that in this section, since it gets confusing having volumes and velocities,
Okay.
unfortunately. Okay, now notice that in that same amount of time dt, the same mass of water had to go through this area of the pipe. Because water isn't compressible. Anything that goes through one end of a pipe must come out the other end. If the pipe's full of water. You with me? So, in dt, probably this water has to get that far to get the same volume here that we have here, right?
Okay.
Okay.
This is still going to be the same dv, or dm, same amount of water, same mass of water right here.
Gotcha.
This right here, so the water here is flowing with some velocity v2. So this distance right here then is
Rho times the area.
this distance,
It's V2 times dt.
just v2 times dt.
Oh, gotcha.
And so dm here is, this dm is equal to our volume times our density. So density times volume. That's supposed to be rho, not p. Rho times our volume. Our volume is going to be A times V2.
A2 times.
Thank you. A2 times V2 times dt. With me?
Yeah.
Now dm is this. So these two equations are equal to each other.
Okay.
So I get rho times A1 times V1 times dt is equal to rho times A2 times V2 times dt.
Yeah.
So you cancel out your rho's and your dt's.
Perfect. And we get our next equation that we care about, which is that A1 times V1 is equal to A2 times V2. As a cross-sectional area in a pipe goes down, the speed at which the water goes through the pipe increases.
Say that again.
As the cross-sectional area of your pipe decreases, the velocity of the water going through the pipe increases.
Okay.
And you have intuition for this already. If you have a garden hose and you want to spray someone, what do? You squeeze it so it has a really small opening, which causes the water to shoot out.
Because it's got to go out the same way it comes in.
Interesting.
Right? Same idea. You already have pretty good intuition for this. There it is explicitly.
That's cool. Why don't we all have all of our pipes massive at the start and then slowly get smaller? That way you can transport it quickly? Or is that what we do?
Sorry, say that one more time.
If you wanted to get a gas line, why don't you make it start out really big and then slope down and get way smaller so at the end it still comes out at the same speed, but it just travels across that entire area faster?
The water goes through the pipe at the same rate no matter what. In the time, the amount of water that leaves this, more water doesn't come out of your hose because you spray harder. The water still comes out of the hose.
Oh.
The same amount of water comes out per second as before.
Oh, okay.
That makes sense.
There you go. Okay. And then one more thing to note here, just in general from this picture, so we can kind of ignore the second half for a second. Say that in terms of V. Okay, we can think about it that way. So once again, dV here was equal to the area there times the velocity there times dt, right?
Mm-hmm.
So sorry, I drew this big picture. That was to come up with this equation. Now I'm going to reuse this picture really quick to give us another equation.
Okay.
So that's what I'm doing. So reset up. This has cross-sectional area A with velocity v of the fluid going through it. We are saying after some time dt, then we have v times dt is the volume of the fluid that went through this, right?
Mm-hmm.
So dv here is equal to a times the velocity of the fluid times dt. Or in other words, the change in the volume with respect to time is equal to the velocity times the area. And we call that the flow rate. So the flow rate of your fluid, dv dt, is equal to velocity times area. And that's fairly intuitive. If I kept my velocity the same, but I increased the area, then more water flows through.
Yes.
If I keep my area the same, and I increase the velocity of the water, more water flows through.
Yes.
So our flow rate increases with the volume and the area, or with the velocity and the area. Good?
Yeah.
Okay. Now, the heart of all this in one picture.
What's the Greek letter for V?
The Greek letter for V.
Yeah, why do we keep doing volume and velocity the same?
We don't. There isn't really a V one that I know of. The Greeks don't have the same alphabet we do. They have less letters.
Shame.
And not all the letters have a natural rollover. What's the counterpart to pi?
I.
And what's the counterpart to sigma? And for lowercase sigma is that.
Of course you know.
So, yeah. We sometimes call things like omega, oh, that's the Greek W, but that's just what we say to help you remember it. Because omega was the last letter in their alphabet.
Oh, interesting.
So when you hear from alpha to omega,
Yeah.
that's the same as us saying from A to Z.
Just sounds cool with alpha and omega.
Well, yeah, to a Greek it probably sounds cooler to say from A to Z. My God, what are these A's and Z's that are being referenced?
Got 26 of them.
Okay, so finally deriving Bernoulli's equations. Okay,
Bernoulli.
yes. And I'm going to set up a similar picture to what we had here before. I'll draw the edge of the pipe first. It's going to go along, and all we know is that at some point it changes. The area changes. So I'm just going to draw like that. Okay, so we've got cross-sectional area here, A, 1, and we've got cross-sectional area here, A2. And we're looking at all the water in between. So I'm looking at this segment of water.
Okay.
I'm looking at some segment of water where the area of the water changes over the interval.
Gotcha.
Okay. Now, what I'm going to calculate is the work done on this volume of fluid from here to here. So,
How is work being done?
in one interval of second, so we're looking over some time interval, erase all this. So we're going to say after some time interval dt,
Yeah.
then the water moves, this one moves, this moves from here to here, and this moves from like here to here, something like that. So this water shifts like that.
Yeah.
Good? And so in dt, some work must have been done on the water to move it. We had this water shifted over. There must have been forces acting on it, and force times displacement gives you your work.
Gravity can be worked, right?
Gravity can do work.
Okay. So yeah, that does make sense.
Is gravity gonna do any work in this?
Probably not.
It
Unless
could
it's
have
the pipe
been. Maybe
down.
this is going downhill, maybe it's not. Who knows? But the point is, over here, we have some pressure on the fluid, pushing this way. Because remember, this is just a segment of water inside of a pipe full of water, right? Inside of some fluid. And anytime you're immersed in some fluid, so when we looked at this area inside of some fluid, then there's pressure acting on it from all sides, pushing in on it, right?
Yes.
So, similar thing even inside of a pipe. We have pressure pushing on it this way, and we have pressure pushing on it this way. With me?
Okay.
Good so far? Okay, what's the pressure over here?
Just your pressure times your area.
Sorry. What's the force? Keep saying pressure. Force. What's the force over here? And you gave me the right answer, even though I asked the wrong question. It's whatever the pressure is here times the area here.
Okay.
Gives us the force here. And because when we're calculating work, we want force times displacement. That gives us work.
Yes.
And ultimately, we're looking for, we don't care about that equation anymore. We're coming up with the equation for the amount of work done in some time interval dt. We're looking at some snapshot over dt, what happened. And we're calculating work. So,
A1 works as like the mass.
A1 is a cross-sectional area of the pipe.
Oh, how does that work with force? Mass times.
No. From here.
Oh, pressure force.
The force due to pressure.
Yeah.
Okay. Because pressure is newtons per square meter. So newtons per square meter times meter squared leaves me with just newtons.
Yeah.
Clicking. Good impression.
A bit.
Okay. And we'll call this displacement over some time t1. We'll call this ds1.
DS1 by DS. Oh, okay.
We use ds for some arc length. This
Yeah.
isn't necessarily, yeah. And then we'll call this one over here ds2.
Okay.
Over the same time dt. And I don't know if we'll need to reference it here. At some point we'll need to reference it. So v1, v1's over here. So v1 is the velocity that this water is flowing with. And it is going to be equal to ds1 dt. And v2 over here is going to be equal to ds2 dt.
What is DW again?
An infinitesimal change in work. That's what we're calculating.
Oh,
The
so
amount of
25.
work done from here to here.
And how do we do that? How do we, over a distance and velocities, how do we find work again?
The simplest way to calculate work for our most straightforward cases is f of x times dx integrated from wherever you start to wherever you end.
So in this case, it would be the force of the pipe times your ds.
This is going to be doing positive work on it. This pressure over here,
Isn't it the same?
no, this is doing negative work on it. That pressure is opposing the motion.
I know, but isn't it this? Oh, never mind.
Positive work, negative work, we're going to calculate the total work
Okay.
that is being done on the system.
Yes.
So this force does, here's the force, here's the displacement. So we have P1 times A1 times ds1 is positive work. This is negative work. So then we have minus P2 times A2 times ds2.
Shouldn't the first part be greater than the second part if it's moving this way?
If it's moving this way, then yes.
Okay.
The work being done here has to be more than the work being done here.
Okay.
Otherwise, water would be flowing the other way.
I know, but you're transporting the same amount of water.
But it's going to be a different amount of work. And so this pressure is going to be less here than the pressure is here.
But the pressure is the exact
No, that was only when the fluid is standing still. With moving fluids, the pressure changes,
Pressure changes.
which is what we're showing right now.
Okay.
Moving fluids cause the pressure to change.
Where's that other?
And so the faster the fluid is moving, the lower the pressure is. What's that?
Where's the other pressure coming from?
This pressure?
Yeah.
Just from the fluid ahead of it.
But
This is in some big system of pipes.
if it's moving that way, how is it putting any forces?
There's water in front of this water pushing back on it.
But the water's going that way.
Doesn't mean it can't push back still.
Okay.
Go stick your hand under a tire wheel as it drives down the road and watch it push back on your hand. It's still going forward.
Yeah.
So the weight of the water is still there, because ultimately what's causing this water up here to move? It's being pushed by this, which is also creating a backwards push like this.
Okay.
Equal and opposite reactions. Okay? And so dW now, we can rewrite this as dW is equal to, now notice that even though ds2 and ds1, those are different, the volume that's displaced here and here are the same. And so this is dV, and this is dV, and those are the same.
Yes.
And so I can rewrite this as P1 times dV minus P2 times dV. Or in other words, the work is equal to P1 minus P2, the change in your pressure, times dV. So that is an infinitesimal amount of work that's done. So there's dW. Now we want to find a change in kinetic energy, I think is the next thing we want here. We're going to come up with 3 little equations and then combine it all together. Okay. So that was the work at the beginning between A and B now. Right. So notice as the fluid flows from here to here, when we're looking for our infinitesimal change in kinetic energy, then what do? As our fluid flows from here to here, we lose the kinetic energy of whatever this part of the fluid has, and we gain the kinetic energy of whatever this part of the fluid has. Because the kinetic energy of the fluid from here to here remains the same. So our fluid starts out like this. After dt, our fluid's right here.
Yes.
So we lose this part, and we gain this part.
But it's the same in volume.
It's the same volume, but we lose the water that was here, and we gain the water that was here now.
Would it not be the same kinetic energy though?
No,
Velocity.
because it's going to speed up.
And kinetic energy is
There you go.
dependent on this.
Okay, so we lose the water that was here, we gain the water that was here. All the water right here is still the same in both pictures.
Yes. That
Okay,
makes sense.
so when we're calculating the change in kinetic energy, we gain whatever kinetic energy this portion of water has, and we lose whatever kinetic energy this portion of water has.
Okay.
So the kinetic energy of this portion of water is going to be 1/2 times the mass of this portion of water, which we can say is rho times dV. Well, we'll be more explicit than that. Is rho times A2 times ds.
Why
ds2. Huh?
Why do you use rho?
Density times volume gives you mass. Kinetic energy, in general, is 1/2 mv squared.
So you're just timing by volume.
We could put a dm there, actually. I think these will... We'll just put a dm here for now. dm times the velocity here squared times v2 squared minus 1/2 dm times the velocity, in a little curler, at 1 squared. And then I guess the way that he ends up leaving this equation is, so dk, well, we'll just write it one more way here. dm is rho times dv, right? So I'm going to factor out 1/2. I'm going to factor out the dm from both these, which is going to be rho times dv, where, keep track in mind, dv, that's volume,
Okay.
times v2 squared minus v1 squared. Okay, there's our infinitesimal change in kinetic energy. And now we need to find our infinitesimal change in potential energy.
And it's just the same process basically, right?
Yeah, potential energy is the easiest one because when you have water flowing through a pipe or fluids flowing through something, all we care about is gravitational potential energy. And so the change in potential energy here is going to just be mass. Remember, in general, gravitational potential energy is mgh, right?
Yes.
So du is going to be m times g times h. H is just going to be the average height of the water at point 2 minus the height of the water at point 1. So in this case, I made it seem like the middle of the pipe stayed the same, but this pipe could have jumped up over some interval of time.
Got you. That makes sense. So why is it only gravitational potential energy and not the other one?
What else could store energy when you just have pipe running through a system? All that
Maybe
actually
you have a
is-
piston on the end of the pipe that pushes it.
Well, that would create work.
Oh.
We're just talking about flowing fluid.
What's your other type of potential energy?
Well, we had like compressing a spring, for example.
But you can't compress water, right?
You can't compress water, but yeah, you also can't compress it and let it go and have it re-expand out as a
Okay.
spring.
Okay, that makes sense now.
Okay. So, now we can combine all three of these. The change in work that we put into a system will result in whatever change in kinetic energy there is, plus whatever change in potential energy there is.
And there's no kinetic or potential energy at the first, so you don't care, right?
This is just a change. There was kinetic energy at the start, there was potential energy at the start. But the change in the work that I do on the system, if I do some small amount of work on the system, then that's going to do some small amount of, that's going to give me some small amount of change in kinetic energy plus some small amount of change in potential energy.
That makes sense.
I put some small amount of energy into the system, that results in a small change in kinetic energy plus some small change in potential energy.
Okay.
So now we plug in these three things. We found a dW, we found a dk, we found a du. Okay, so dW was P1 minus P2
Times dV.
dV
Yeah.
is equal to 1/2 rho times dV times V2 squared minus V1 squared plus rho times dV times G times Y2 minus Y1. Good so far?
Yeah.
So you can cancel out your dVs.
Perfect. So P1 minus P2 is equal to 1/2 rho times V2 squared minus V1 squared plus rho times G times Y2 minus Y1. Now, if we want, we can put all our terms that have a sub 1 on one side of the equation and all the ones that have a sub 2 on the other side of the equation.
Okay.
Why
Which
would
is-
we want to do that?
Because then it shows us how the start is relayed to the end. So here's finally Bernoulli's equation. P1 is equal to, or P1, no,
Just P1.
sorry, P1 plus, move this to the other side, click my V1 term here, which is 1/2 rho times V1 squared. And then this term, we have rho g times -1y is going to be plus rho times g times y1, that's a rho, is equal to P2 plus 1/2 rho times V2 squared plus rho times g times y2.
That's quite the equation.
It's quite the equation, but notice what it says pretty simply. It kind of says, it doesn't quite say this, but it almost says this, since we took the dV out. It says the pressure plus the kinetic energy plus the potential energy is a constant. Doesn't change. Whatever it is at point 1 is what it is at point 2.
Oh. Even though your kinetic and potential energies change?
Yeah, those individually can change, but the sum of all three together is a constant.
So
It's kind of like an energy conservation law, almost. This isn't quite energy because we canceled out those dVs, but if we didn't, it would be an energy conservation law. So this isn't technically energy.
So now that we know it's constant, what can you do with it? Like how?
You know it doesn't change from point to point.
Yes.
So if I know P1, V1, Y1, and I know P2 and Y2, I can calculate V2.
Oh, I see.
And so that's Bernoulli's equation, and that's, I think, our last equation that we have for today.
Then they have like 2 more sections.
That's it. Yeah, that's the last one that we have for today. Bernoulli's equations.
Okay.
But I did want to talk about airplanes, and before we talk about airplanes, be good to do an example problem before the airplane to see something crucial.
You mean one of these example problems? Using
Yeah.
this stuff? Okay.
Yeah, so I'm going to do example problem 12.9 because I think it sets us up well for talking about airplanes and how an airplane flies. And maybe we could write Bernoulli's equation right here. P1 plus 1/2 rho times V1 squared plus rho g y1 is equal to P2 plus 1/2 rho times V2 squared plus rho g y2. Okay. So now let's do this example problem, and hopefully I can draw this picture half decent. That marker's coming down on me. Okay, so we'll have it do that, then it'll come down, then we'll do that. I guess it doesn't really matter if it's symmetrical, but looks nicer. Okay, so we've got some pipe rushing through, water rushing through some pipe, so the water's flowing this way. And up here, I have a tube in the pipe. Just sitting there, and this is just open to the air out there. So water's just gonna flow into this pipe. There's gonna be some amount of water in here.
Okay.
Water's flowing this way. Over here, I do something similar. We'll do it after where I draw my areas, so give myself some space. call A1, cross-sectional area A1. This one we're going to call cross-sectional area A2. Intuition check. How is the water in this pipe going to compare with the water in this pipe?
Same water level.
Same height?
Yeah, that makes sense.
No, it's going to be lower.
Why?
It's because you're.
Because your pressure goes down as your velocity goes up.
Okay, that makes sense.
As the water flows faster, you get less pressure.
Why isn't the
And so
water
there's
in
going to
there?
be a height difference here of h.
Isn't the water in there just gonna be the same? Like not moving?
The water in here isn't moving, but what's holding up the water is the pressure from down here. So it depends on what the pressure is here to determine how high this water goes. And the pressure here is higher than the pressure here. And so this is the type of instrument that we use to actually measure the pressure difference between 2 points in a pipe.
Okay. In
Based
case
off
if you
of
want to
how
know
high
whether
water
it
is.
would break or something.
Say that again?
I said in case if you want to know whether the pipe is going to break or something.
Or just to measure it. There's lots of reasons you could want to measure pressure differences.
You know, if you're just bored.
Well, maybe you need some minimum pressure for certain heights of buildings that you're going to provide plumbing to, and maybe someone's wondering, hey, is it possible for your plumbing system to support a 4-story building or whatever?
Oh, I see. Okay.
Because getting water up, think about what we have to do. How do we get water up 2 stories? We already discovered that even with a perfect vacuum sucking, you could only lift water 10 meters.
True. How do you do that?
How do you provide water to these buildings? And so you need ways of building up enough pressure to push it up high enough. You can't suck it up, you need to push it up. But, anyways,
It's just gonna have more weight in the atmosphere.
well,
Pushing it.
there's 2 ways I could have you try and get water up 11 meters in the air. I could have you go stand there with a straw and suck till you die and never get it up. Or you can just grab a bucket and haul it up. Somehow push it up. Rather than relying on the atmosphere to push it up. That makes sense. Doesn't matter. Whatever reason, we want to measure the pressure difference. Okay. So let's actually read the problem. Figure, like I've shown here, we didn't do the velocities. This is flowing with the speed of v1. And this is flowing with the speed of v2. Okay, so I think I've drawn the figure now. So this figure shows some type of meter used to measure flow speed in a pipe. Oh, so let's just measure the flow speed. Because since those are different heights, you can calculate the different pressure, therefore calculate the flow speed.
Oh, got you.
Derive an expression for the flow speed V1 in terms of the cross-sectional areas A1 and A2 and the difference in height H of the liquid levels in the 2 vertical tubes. So we're actually trying to measure flow speed here.
So we're just going to use that equation and then solve for V1?
So we're going to use this equation here, and then we're going to use the fact that we know that these are as high as they are to figure this out. So using this equation, first off, we're going to assume that the average height of our water doesn't change going from here to here. Tried to draw that, but that might not be intuitively clear. So potential energy of the water doesn't change, is what I'm trying to say there.
Okay.
So we have the pressure at 1, pressure here, just using this equation, sorry, I'm kind of covering it up as I write, plus 1/2 the row of water times V1 squared is equal to P2 plus that. Is equal to P2 plus 1/2 rho times V2 squared.
Oh, you're saying since your potential energy is consistent, then you can just cancel them out?
Yeah, we're assuming that potential energy here doesn't change in any significant way. Okay, so here's one equation that we have. We're trying to write an expression for V1 in terms of V2? Oh, just the expression of V1, we need to get rid of the V2. So we're trying to figure out what V1 is here.
How do you get rid of V2 then?
I don't know yet. So let's think about what else we know. First off, we know that these two pipes differ by a height of h, right?
Yeah.
The height here is produced by P2. The height here is produced by the height here is produced by P1. The height here is produced by P2.
Okay.
And so I know that P2, P1 minus P2, the bigger pressure minus the smaller pressure, is going to be
Your negative P times G times H?
almost just rho times G times H, since I changed the order that I wrote those in.
Oh, I see.
I didn't do P2 minus P1, I did P1 minus P2.
Yeah.
Okay? So that gives me a relationship between P1 and P2. And so which one do I want to substitute out? Maybe substitute out the P2. So I'll say that P2 is equal to P1 minus rho times G times H. Right?
Yeah, that makes sense.
So, substituting that in, let's see what we got so far. We have P1 plus 1/2 rho times V1 squared is equal to P1 minus rho times G times H plus 1/2 rho times V2 squared. So, that enables us to cancel out the P1 with the P1, right?
Yeah.
And we can also divide through by rho. And so far, and I'll multiply through by 2. And so I'm going to get V1 squared is equal to negative 2GH plus V2 squared, right?
Okay. So now you're trying to figure out what V2 is?
Now we got to get rid of V2 somehow. And how on earth will we do that?
G.
I wonder.
I'm lost.
What if
I
you
wonder what equation we could use to...
Yeah, you're obviously pointing at that equation, but that has to do with velocity, and that has to do with
Alright.
volume.
You just have to.
No, oh, these are velocities. Okay, no wonder you're confused.
Okay,
Yep,
that makes more sense.
that's a velocity. That's a velocity. Okay, yep, those are velocities.
Okay.
Okay, so now we can do a substitution and we can rewrite V2 in terms of V1. So we can rewrite this equation as V1 squared is equal to negative 2GH plus...
A1 times V1.
We're substituting out V2, so it's going to be A1 over A2, right?
Yes. Oh, okay, yeah.
Yes.
Yeah.
I'm substituting out V2 for V1, so A1 over A2. So it's going to be A1 over A2 times V2 all squared. V1.
Yeah.
All right, I didn't do anything wrong, right? Let's not make just one stupid little mistake. And so, why did I put my G in the denominator? Minus 2GH, I have no clue why I did that. Okay, and so now we get our flow rate V1 is equal to the square root of, we'll write this term first. We'll just say A1 squared over A2 squared times...
You need to get V.
What am I doing?
You're solving for V1.
You have to get the V1 on the other side first.
Yes, obviously, that is what I have to do. Why am I not doing it? That's a good question. Okay, so I'm going to move this over here and this over here.
Okay.
But I'm going to write this side first. So we have this term. We have A1 squared over A2 squared minus 1 hopefully you can follow this all in one go.
Yeah.
V1 squared is equal to 2gh. So I put these two together, factor out the v1 squared. So when I factor out v1 squared from this, that's going to be minus 1 since I moved it to this side. When I factor v1 squared away from this, that just leaves us with that. And so it comes out like that.
Okay.
Follow the algebra there?
Mm-hmm.
Yeah.
Okay. So now, we're basically done. Let me see how he writes his answer. I'm wondering if I should split up that A1, A2. No, he doesn't, so I won't bother either. So now just divide through and take the square root. So the answer he has is V1 is equal to the square root of 2gh divided by, should we make this bigger? Divided by A1 divided by A2 squared minus 1. Good?
Yep.
Okay, so this didn't set us up as much as I thought to talk about a plane. So that's too bad. Oh, and I didn't bring my ping pong ball and funnel. I can't believe I forgot that for this class.
Ping pong ball and funnel.
Yes, ping pong ball and funnel. To give you a demonstration of how pressure and velocity are inversely related. So this is something you can do at home. Get a ping pong ball and a funnel. And I want you to try this. So you're going to hold your funnel upside down. So your funnel looks something like that.
Yeah.
You're going to have a ping pong ball inside of there. You're going to hold up the ping pong ball. You're going to blow down as hard as you can on that ping pong ball. And maintain it as long as you can and let go of the ping pong ball. And the ping pong ball is going to stay up inside the funnel. I know you don't believe me, but that's what's going to happen.
Is it on the ground or something?
No.
If you
That's
hold
exactly
it up, though,
what
it's
you're
just gonna
talking
fall. So you have to blow the instant you let go of it.
Start blowing and then let go. So I hold the funnel up to my lips, pointed down. I take a ping pong ball, stick it in there. I start blowing. Let go of the ping pong ball while still blowing. It will hold the ping pong ball up as long as I can keep blowing.
In the funnel?
And if you can hook like a pump up to a funnel, something that continually blows, then you can just stick the ping pong ball up in there and watch it just bounce around.
But you have to keep blowing, right?
You have to keep blowing to hold it up. Obviously, you can't hold up a ping pong ball unless you're blowing down on it. How else do you hold up a ping pong ball?
How does that work?
How does that work? Huh?
Is it because the air goes around it and then pushes
Nope.
up?
The air can't go around, it's going down.
It's going down. What that does is the air up here is moving. So when you blow down, the air up here is moving like this around the ping pong ball,
Why
right?
doesn't it just hit the ping
Yeah.
pong ball?
It does hit the ping pong ball, and there is some air force pushing down on it, and that does happen.
And
But-
that's all.
All other things being equal, where's the best one that shows it? Where's our best equation for showing that pressure and velocity are inversely proportional?
Inversely proportional.
Inversely proportional. Yeah, we don't really have one that shows it right out the door. But since I guess we have it with this one. Notice that what happens as a pipe gets smaller, the water speeds up.
Yeah.
So by making it smaller, what we're really doing is we're making the water speed up. And by making the water speed up, we drop the pressure of the water.
Mm-hmm.
Okay.
So what happens is when you blow on the ping pong ball, the air above the ping pong ball is moving a lot faster than the air right here directly below the ping pong ball. So below the ping pong ball, we have some pressure P1. And above the ping pong ball, we have some pressure P0. And by blowing down, you make P0 a lot smaller than P1, creating a buoyant force pushing up on the ping pong ball.
What about the fact that P1's pushing against it?
There could be a buoyant force in the air.
There is a buoyant force in the air. Air is a fluid.
Yeah.
Right now, the air is pushing my arm up. So an absurdly small amount, but it's pushing my arm up. And compared to gravity, it's nothing. We calculated the buoyant force on a little gold statue that weighed 15 kilograms.
Yeah, we did.
And it was absurdly small, but it was there. When you drastically change the pressures like this, now you create a much bigger buoyant force on that ping pong ball.
Yeah, you do.
So, if we were to draw a free body diagram for the ping pong ball, you have the weight of it pulling it down, which is why it's important that it's a ping pong ball, something that doesn't weigh a lot.
Okay.
You have the force from your blowing pushing it down, and then you have the buoyant force pushing it up. And the buoyant force can be big enough to cancel both those out if you blow hard enough.
You have so much more force pushing it
No, you don't.
down.
The pressure difference is big enough that holds the ping pong ball up.
You're
I know. You're blowing on it.
Interesting.
And you can also notice a similar thing. This one's one you can also do. You can do this one with a hairdryer and a ping pong ball.
Yeah, I know. Pop it up, right?
Not even just pop it up. So here's the hairdryer. Well, this one's slightly different, but it's a similar concept. So here's my hairdryer, and it's pointing up in the air.
yeah.
And I've got my ping pong ball right here. And the hairdryer is blowing. Well, as the hairdryer blows on the ball, the air on the ball goes like this. Around the ball, right?
Okay.
Also pushes the ball.
It pushes the ball up, but what's important, think about if I had a ping pong ball and I sprayed it with a hose, and I tried to hold the ping pong ball up with the hose. How hard would that be to stop it from landing on the ground?
Pretty difficult.
That would be absurdly difficult. Do it with a ping pong ball with a blow dryer, and now, while you're holding up, poke the ball, and it will fall back into the center. This is stable. It will hold the ping pong ball at the center, because the air moving around the ball is so much higher, is moving fast, and so it's low pressure around the ball, but the air over here is high pressure. And so there's a net force pushing in like this, and a net force pushing in like this, forcing the ping pong ball to stay above the blow dryer.
That makes sense.
Why doesn't the air pushing the blow dryer overcome that buoyancy force and push it off and make it fall?
Yeah, why doesn't it do that?
Because the pressure difference is greater than the air just pushing on the ping pong ball. The air just pushing on the ping pong ball isn't enough to overcome that buoyancy force.
Buoyancy force can work down too, right?
It can work any direction.
That is so weird. So in
It's
water.
just where there's a pressure difference.
Okay. Okay.
The ball's being pushed up by a hairdryer.
The ball's being pushed up, so okay, that's fine. But it should also, more air should be hitting slightly on one side of the ball than on the other. And so it should be pushing the ball this way as well, or pushing the ball this way as well. Like me spraying a ping pong ball with a hose. If I were to try and spray a ping pong ball with a hose and hold it up, yeah, the ping pong ball is going to go up, but I can't stop it from flying that way or flying that way because of how hard the wire hits it. But if I did that with air, now I suddenly can.
Yeah, that can make sense on the hairdryer. Doesn't make sense if you blow them down on the ping pong ball and it's not sealed or anything and it still stays there.
Yeah, it's very intuitive and something you can easily try for yourself.
You should have bought it.
I wish I remembered to, because it's a cool one to do.
You should go get it.
Even if we just have a ping pong ball, we could just make a funnel out of a piece of paper and
Yeah.
see it.
You can do it with a piece of paper.
Yeah, you just need something in a funnel shape.
Too small.
Okay.
Anyways, so now let's talk about how an airplane stays in the air.
And it's the same concept?
Yes, similar concept. If you look closely at an airplane's wing, if we look at it from the side, so the airplane's wing looks something like on the bottom it's flat, you'll notice, and on the top it actually curves up like this and goes like that. An airplane wing looks something like that if we're looking at it from the side. So here's the front of the wing, here's the back of the wing, the airplane flies this way.
This is in the body.
And we're
this is
looking
the
at
wing.
the wing side on like this. The
Okay.
wing, one of the wings of the planes.
Gotcha.
You guys me so far?
Mm-hmm.
Okay. As the plane moves forward, try and draw some flow lines on this plane, I guess. The flow lines on this plane for the air beneath it, the air just flows like this. Nothing weird happens because it's flat underneath the wing, right?
Yeah.
The flow lines on top of the wing look like they're going to kind of hug it, and then that one kind of hugs it, and that one kind of hugs it. And what the shape of the wing causes to happen is as the wing goes forward, the air that flows on top of the wing moves much faster than the air going underneath the wing.
Why is that?
It's kind of like the same thing that happens here, where you're compressing the pipe together. We're kind of slowly compressing the air up,
Okay.
which is increasing the speed of the air.
That makes sense.
And so that compression causes the air to travel faster over the top of the wing than it does the bottom of the wing, and therefore makes a pressure difference. And so the pressure above, at the top of the airplane's wing, the pressure up here is actually lower than the pressure down here. And so it creates an upward push on the airplane's wing. An airplane is not just gliding. It does not operate the same way that just a glider operates.
Yeah.
The wings actually create an upward pressure on the plane.
So really, we
Keep the
don't
plane
even
in
need
the
jet
air.
engines?
Why do we need jet engines?
Oh,
Speed!
keep it moving.
Faster, faster, faster. The faster we go, the greater the difference, the more upward thrust there is.
So if you want to go up in an airplane, you just have to increase speed?
Well, kind of. I mean, this is still directed. You can still direct it.
Interesting.
The same way that just because I push a boat forward doesn't necessarily mean it goes forward. You can just turn the rudder and cause a boat to turn. So just because there's a push upwards doesn't mean it necessarily goes upwards, and there's ways that they can control how it goes up, how it goes down. But that's what holds it up in the air. And yeah, the faster you go, the more you can hold it up. So that's how airplanes work. Now we won't do anything with viscosity. We won't solve any problems with viscosity, but we'll just talk about viscosity. We've been idealizing all our fluids so far, and we've been kind of like ignoring internal friction between the fluid. Oh, before we talk about that, let's talk about one more instance of these pressure differences. Because these pressure differences are also what create curveballs.
You mean in like baseball?
In like baseball, or in like ping pong, or in like golf. In all these scenarios, you have curveballs which change the path of the ball. How does that work? You know how to throw a curveball. What do you have to do to throw a curveball?
You spin it.
Spin it. How come spinning creates a curveball? So let's imagine a ball flying through the air, and it's spinning this way.
Okay.
You with me? So now the air that it's moving past, here, so here's the air lines that it's moving past. Up here, since the ball's spinning this way, it's kind of like hitting into that air, slowing down the air up here. That's passing the ball, right? Since it's turning this way, as the air goes past, it's like slowing down the air.
Okay.
Down here, as the air goes past, it's actually speeding up the air.
Where is that?
It's turning this way.
Yeah.
So the ball's being thrown this way, right?
Okay.
And so the air is moving this way, relative to the ball, right?
Yeah.
Since the ball's spinning, at the top, the ball's opposed to the direction of motion. And so it's going against the air molecules and slowing them down. At the bottom, the ball's spinning with the direction of motion.
So it speeds it
So
up.
it speeds it up. So you have less pressure,
Okay.
more pressure. And so it creates a net force pushing the ball. So if this was like a bird's eye view of because you know in baseball when they try to do it, they try and spin it on the side. They don't spin it from the top. Well, I guess they could to cause it to go down faster, but if I spin it from the side, so if this is a bird's eye view and I spin it from the side, that's going to cause my ball to move. We have lower pressure here, so it's going to cause my ball to move that way, the direction that you spin it.
Yeah, that makes sense.
And so that's how a curveball works.
So curveball is dependent on buoyancy?
It's dependent on the fluid, yeah. I don't know if I should be calling this buoyancy all the time. It's dependent upon the force due to pressure differences.
Pressure differences. Okay.
Yeah. A pressure difference causes a force. That's what keeps airplanes in the air. That's why you can blow down a ping pong ball and hold it up. That's why you can hit a spin ball in ping pong and the ball will take off the direction that spins.
Interesting.
Okay, so talking about curveballs and spinning stuff. And then so the last thing we want to talk about was just viscosity. And viscosity is just the internal friction between fluids. Honey has more viscosity than water.
Yeah.
There's more friction in honey's flow than there is in water's flow.
Internal friction.
Between
How does that
the
work?
molecules. There's just friction between the molecules. And
There
the paths
could
that
be
they're going
friction
on.
between atoms.
Sure. Tons of all friction's ultimately between atoms.
How does that work?
Same way that there's friction between me and this ink. There's friction between atoms. It's just on a small
How
scale.
do atoms pull against each other to cause friction like that?
They just rub against each other, bounce off each other, rub against each other. Kind of stick to each other a little bit.
I'm saying, yeah, why do they stick to each other a little bit and not just no friction at all, you know?
I mean, part of it is, for example, water has a charge.
Okay.
So two water molecules are going past each other, and they might kind of stick a little bit. And then keep moving though and overcome it. And so they kind of both lost a little bit of their speed because they kind of stuck to each other a little bit. There's a little bit of friction there.
Okay.
And that's going to come off as heat or something in that interaction.
Okay, that makes sense.
So there's friction between everything. And so we call that viscosity, the internal friction of a fluid. Higher viscous fluids have a less of a flow rate. Lower viscous fluids have a higher flow rate. All other things being equal.
Is there a fluid that has no viscosity at all?
There is a notion of a superfluid. And I think a superfluid can be said to have no viscosity. I'm pretty sure. Superfluids, yeah, there's no viscosity, there's no friction. Superfluids are super weird.
So how do they stick to each other?
You put them in a container, it's hard to contain a superfluid. You can see with the superfluid, if you put it inside of a container, and you have a superfluid inside of here, it will kind of just work its way up and out of the container.
Against
through
gravity?
Against gravity, but that's because it just takes a lucky random bounce for one of those things to kind of get going and start taking off. And since there's no sticking to overcome that random bouncing, then it kind of just slowly works its way out.
So you have to contain it all the way?
Yeah, it can be a little bit tricky to contain.
And then how do you know that it doesn't just like kind of bleed out of the container?
I don't understand the question.
Oh, that doesn't work. Never mind. Yeah.
How do you make it?
Superfluids?
Yeah.
Well, I'm not positive, but one of the conditions is going to be that you have to have it at almost 0 degree. Zero. Absolute zero.
Absolute zero.
Yeah, absolute zero is
What
0
degrees
degrees.
is there?
I don't know if we've really talked about this. We talked about more in thermodynamics, but roughly speaking, there's three units that we use to measure temperature. We use Fahrenheit, we use Celsius, and then we use Kelvin.
And so you're saying when Kelvin reaches 0?
0 degrees Fahrenheit is just based off of what's the coldest conditions some guy during the Enlightenment could produce in his laboratory. The coldest condition he could produce, he called that 0.
Okay.
0 degrees Celsius is based off of when water freezes at sea level.
Yeah.
Yeah.
And 100 degrees Celsius is based off of when water boils at sea level. 0 degrees Kelvin is absolute zero. It's when you remove all energy from some volume of space.
Yeah. The coolest thing.
And theoretically impossible to produce. You can only get really, really close to it. And so matter at very, very low temperatures behaves very, very strangely. Roughly speaking, there's 5 states of matter.
5 states?
Yeah. We're kind of done with lecture material. I don't know if we really
Are we
care
not
about all
doing
this.
chapter 13?
Oh, we still have a bit of time left, don't we?
An hour.
I mean, we could.
No,
cover some of
we'll start chapter 13 next time. We'll just call it there for now.
Okay.